So I want to present my lecture, Advanced Measure Theory, which will be held in spring 2020-21. Well, I will focus in my lecture on geometric applications of measure theory. By that I mean applications in an analog of differential geometry. So the subject of our lecture will be the study of subsets of Rn. Everything will be a subset of Rn, and I will assume they have dimension k, which is less than n, less or equal n. So first of all, what are k-dimensional subsets? The measure theory is about the approach of measure theory is to assign with every set sigma some kind of a measure, and then assign to this measure a functional of this type. So just integrating with respect to this measure. Then we can test properties of the measure by plugging in here different functions f to see different properties of mu. This is a fruitful approach that is also very elegant in mathematical terms. So you can find proper geometric properties of sigma with by testing mu against some function f. So, what are k-dimensional measures now? Because we are asking what are k-dimensional measures. Well, first let us look at the Lebesgue measure. So we look at the Lebesgue measure. It is characterized by three properties. It is Borel regular. Second, it's translation invariant. And third, the measure of a cube, say, is 1. So it's normalized in a sense. So if you have any measure with these three properties, then you know it must be the Lebesgue measure. So in case k is less than n, we would like to have a measure that mu that's satisfying 1 and 2, and so the measure of a manifold should be equal to the surface measure. Whenever M is a manifold, differentiable manifold. So assume you have a measure that is Borel regular, translation invariant, and has this property that it coincides with the surface measure if you measure a differentiable manifold. It turns out that this does not characterize uniquely any particular measure. There are different choices of measures, but any such measure should be understood as being k-dimensional, right? It gives you the third condition, that it coincides with the surface measure on k-dimensional manifolds of dimension k, right? This should be the proper notion of a k-dimensional measure. And it turns out that there are different choices. You have many different choices, but we will focus on a single one, or maybe two of them. So there is this Theodoric construction. Theodoric construction, which, so as input, it takes a set function, so a function non-negative function which assigns to every subset of x is another set, some number, and it gives you a measure over x. So x is Rn. In our case, it will be always Rn. So if you take zeta to be, well, up to some constant, the diameter of the set to the power s, then this gives you the Hausdorff measure. Hausdorff measure. But there are different choices, and if you, and they will always have they will always be Borel regular, and they will be translation invariant, like construction, and they will you can construct many measures which have this third property that they coincide with the surface measure on any manifold, k-dimensional manifold, but they are kind of different on other sets. So this is the main and most important example is the Hausdorff measure, but there is also a different choice, so-called Favart measure. This is Favart measure, which is also called integral geometric measure. These two are kind of most important choices of k-dimensional measures in Rn. And then once we have the notion of the Hausdorff measure, we can define what is the dimension of the set. The Hausdorff dimension of a set is just the infimum of those as real numbers, such that the s-dimensional measure is 0. Okay. So and this defines what does it mean to be a k-dimensional set. K-dimensional sets are exactly those which have Hausdorff dimension equal k. Okay. So recall that we want to do geometry. So, and by doing geometry, I mean that we want to implement this approach that with any set we assign a measure. This will be basically you can assign a k-dimensional measure restricted to sigma, something like that, and then you want to study properties of this measure of the set by studying properties of this functional. So what we want to do is to integrate functions with respect to this Hausdorff measure. How do you integrate a function? So you already know that you have how to integrate a function. Well, there are several approaches, but there are in general you can do three things. You can integrate by substitution. Substitute. You can do Fubini, and you can do by parts. Integration by parts. And these three options work very well for k-dimensional manifolds in Rn, but we would like to do these three tools also for more general sets, not only manifolds. So we introduce this so-called HKK rectifiable sets. So we say that sigma is HKK rectifiable if and only if you have some collection of C1 manifolds, a countable collection that it covers sigma up to a set of measure 0, where Mi are differentiable manifolds. Manifolds of dimension k. So You can cover up to a set of measure 0 by a countable union of differentiable manifolds of dimension k. Then this set is called HKK rectifiable. Usually you assume also it has finite measure. Okay, so for this class of sets, this is a large, evidently a larger class than just manifolds. For this set, you have the area formula, the co-area formula, and the Stokes theorem, which correspond to integration by substitution, so change of variables. Co-area is the Fubini, and Stokes is a Stokes, as you know. So the main goal of the lecture will be to prove 1 and 2, area and co-area. About Stokes, I will not say anything because we will not have time for that. But even having area and co-area, this is enough to do a lot of things and to prove quite nice corollaries. We can then look a bit at sets of positive reach, so-called sets of positive reach. We can characterize them with Steiner formula. We can prove Bezikovich-Federer projection theorem, which characterizes purely unrectifiable sets. We can see that the Hausdorff measure is not a product measure. We can from the area and co-area we can deduce many interesting things. And if time allows, we will talk about this in the lecture. Concerning the exam and exercises, there will be some homework to do, some talks to be given in the exercise sessions, and there will be take-home exam, and then an oral presentation, and this will be it. So I think it won't be so hard. You are all cordially invited, and thank you for your attention.